We have a first review talk by Dan Milisavljevic. He will give a talk on the connection between supernovae and their supernova remnants.
Thank you for the introduction, Ilse, and thank you for the invitation to come here today. This is a topic that I find of great importance, and I think as a community we should really be riding the wave of energy that's happening in the transient community. No joke, coming in through the port of entry today, going through the Border Patrol, they asked, "What are you here for?" I said, "I'm here to give a talk at the Royal Astronomical Society." And they said, "Oh, what's a topic?" You know, being very inquisitive. And I said, "Exploding stars." And he said, "Oh, supernovae. I know all about that." I said, "Wow, that's right." And he said, "Oh, we're academic equivalents right now, aren't we right now?" So with gravitational wave emergence and the emergence of time domain astronomy kind of blossoming in the era of ZTF and LSST and the not too distant horizon, there's a lot of energy in the field. And a lot of energy in the extragalactic case through which the supernova remnant people can ride on along with as well. So, without further ado, on my first slide there is Cassiopeia A, which is a remnant that I think will be showcased quite a bit in this discussion today. When I look at something like this, or many of the other remnants that I'm going to show you, I want to understand what kind of star was there beforehand, and I want to understand the explosion mechanism. What is the explosion process that gave it the shape that we see it today? And we'll see that understanding that, one has to involve a lot of fields of research, stellar evolution, understanding progenitor systems, explosion dynamics, dust formation and destruction, all of which I hope to cover with today. Before I go any further, I have to acknowledge the legion of supernova superheroes that I work with, including, and do we have a laser pointer of sorts? No, we don't. Okay, no problem. The Boilermakers at Purdue University that have joined my group there in the center. I wouldn't be able to do what I do without their input. And the group comes and goes as needed. So, the importance of the supernova remnant connection. The motivation is that extragalactic supernovae are unresolved, right? And galactic supernova remnants are resolved, which means you can have complementary information. So extragalactic, you have many for which you can understand things like rates and their peak mean ejecta velocities, whereas supernova remnants, you can actually see what's going on. You can resolve their ejecta and get much more detail than you can from dots. So, you know, broadly speaking, you can have a lot of dots. This is many but distant. Or you can have a few up close, for which you can actually resolve the ejecta and do a very close dissection of their kinematic and chemical properties. So, there we go. There's a game that we play in trying to match the supernova remnants in nearby proximity, our galaxy, and understanding what the original explosion type of what it was. Now, this is finicky because the supernova classification system is specifically made when you have optical spectroscopy of the supernova when it is most luminous. Now, at this historical events, only for which cases where we have light echo spectroscopy can we make this classification secure. So this happens in the case of Tycho's supernova, and for which we can confirm it with the type 1A, and Cassiopeia A. Right? For the others, the classification is a little bit more fuzzy, and there's various ways that we go about this. We can look at its elemental abundances. If it's abundant in iron, it tends to be type 1A. You can look at the morphology. You can look at the iron K emission luminosities in centroids. And you can try and make connections between the various types. But there's always a fuzziness, and there can be a debate between which is the most appropriate. And some of them seem to cross. So for some time, W49b was thought to be as a type 1A, but more recent analysis with Laura Lopez favored the idea that this was actually a kind of a jet-driven supernova, potentially related to the class that are associated with GRB explosions. And the same with RCW86, thought to be a 1A, perhaps interacting, but paper not that long ago associated with the calcium-rich transient. Okay? So the point here is without light echo spectroscopy to give you that original optical spectrum when it was most luminous, there's uncertainty. However, we're getting better at making connections between the remnants and their original supernova types. Oh, and then finally Kepler's. I often see this portrayed as a beautiful core collapse supernova, and I guess just the shape of it makes it that way. And Stan Woosley's code is funny. It's called Kepler, but it's for core collapse, because at some point I assume he thought it was a core collapse explosion. But of course, type 1a. Okay, there it is, Cassiopeia A. And I'm going to show something that doesn't get shown very often, and if we can dim the lights, because I think this shows it the best. This is an animation of 50 years, approximately, of Cass A observations, dating back to the Palomar 5 meter and going, yes, into the HST. And a few things to show here. Whenever I look at this animation, I see something different. But the remnant it was 50 years ago is not the same of what it is today. Okay? It's kind of living in a sense, right? And I'll go through the parameters. The forward shock wave encounters surrounding material. That induces a reverse shock, and the reverse shock is exciting, and this is in the optical, so we're seeing sulfur and oxygen-rich material that's being lit up by the reverse shock. And I wish I had, but can you notice that straight line? It's called the Minkowski filament, that one edge there. And you see that the expansion is going out radially. So something like a feature like that is very interesting. Oh, okay, very good. Let's see if I do, which button?
Top one.
Top one. Yeah, right there. This filament here. Do you see how this expands outward like this, but you know, the overall radial sense is like that? Okay. This is a multi-wavelength look at Cassiopeia A, and it shows certain things, including the forward shock, very dimly lit here in the blue in the X-ray. Okay, so that's the original blast wave of the supernova. We have in the center the central compact object, a quiet neutron star with interesting properties. And I mentioned the reverse shocked, what we call the main shell. Okay, so this is the reverse shock that develops as the forward shock wave moves outward. And then in the northeast and southwest regions are these high velocity outflows that we don't often enough get to talk about. If I have time, I'll briefly touch on it here today, where we have material that's racing out at 3 times the velocity, upwards of 3 times the velocity of the main shell. The main shell is about 5,000 kilometers per second. This is upwards of 15,000 kilometers per second or more. We actually don't know the full extent of the northeast jet. And of comparable distance away, though of less material, that may be due to extinction in some part, or less mass in general, there's this southwest component as well. Historically, they've been referred to as jets. You may hear me say that expression. They are not true jets. They are not highly collimated. The half opening angle is more along the lines of 40 degrees, so almost 90 degrees in total. It's more like a splatter in either direction. Okay, as I mentioned, light echo spectroscopy, a crucial component of our understanding of Cass A. So the original light of the supernova, you know, the shortest path was coming directly towards us, but some light got bounced off by dust clouds in other directions and then took longer to get to us. And we actually have multiple vantage points of the supernova. And this gives us a direct sign of asymmetry because the profiles, the peak expansion velocities in the opposing directions were not the same. So one can do a lot of interesting science with this. You can compare what the supernova looked like at the time of explosion to what its morphology looks like today. You can also compare these various P cygni, so the expansion velocities in the various directions, with the diversity in the type 2b supernova explosions we see extragalactic. So when you look at the variety of optical spectra of the extragalactic cases, for which we have many dozens at the moment, there's a diversity in their expansion velocities. If you look at that diversity, which is broadly represented as the gray shaded region here, and you look at the light echoes associated with the different directions in Cass A, we can see that the diversity fits. So some of the diversity associated with the ejection velocities of extragalactic supernovae can be associated with true asymmetry inside the actual explosion. All right, I'm realizing I'm already going over time, so I'm going to try and pick out the key things I wish to highlight, and I think this will be a theme as we move forward with the excellent discussions today. One is that the remnants that we look at, in particular Cassiopeia A, for which we have a lot of information, they both do and do not jibe with what we understand of extragalactic supernovae today. So, case in point. People whose day job are looking at the progenitor systems of type 2b supernovae. So they look at extragalactic systems, a supernova goes off, they look at the HST archive to look at pre-explosion images and try to see what stars were there beforehand. When they play this game, they say, 2b's must be associated with some kind of companion star, right? Often a B star, that helped in the stripping process, because a 2b means it has relatively little hydrogen at the time of explosion. However, when we peer deeply at the center of Cassiopeia A, we do not see an obvious surviving companion star. Right? So here is a case where we know that this is a type 2b explosion. In fact, its optical spectra have been matched with 93J. The people who look at 93J today say, yes, we are fairly confident that there's a B star at the location. That B star aided the original progenitor star in losing its envelope. But in the case of Cassiopeia A, we do not see that star. Right? So now we have to think, well, what's going on? Are there are there multiple channels for a type 2b supernova? I don't like that. Are we not looking close enough in either Cassiopeia A or in the 93J system? Right? One cannot ignore, let's say, one cannot ignore what Cassiopeia A is telling us. And what's allowed at the moment is systems where Cassiopeia A progenitor star evolved with a neutron star or black hole. Now that's rare, but it does happen. Or there is a merger. Okay? We don't often think of mergers in type 2b systems, but Cassiopeia A is saying that's a very strong likelihood. Okay, moving on. What else can we do with Cassiopeia A? And comparing that remnant to extragalactic supernovae, right? Leveraging what we can see in the resolved case with a distant unresolved supernova. In blue is an integrated spectrum of Cassiopeia A. So my PhD work, I marched a long slit across the entire remnant and then integrated it, simulating what the remnant would look like as an unresolved source. And then compared that to what 93J looks like today, approximately 16 years, well, at the time of observation, 16 years after explosion. And so we can actually see what the evolution is going to look like from 93J. So right now, there's a lot of hydrogen-rich material, but that reverse shock is going to be moving inward, and it's going to pass through that hydrogen-rich envelope at some point and start exciting the sulfur. Okay? And it hasn't and here's the sulfur in Cassiopeia A. We're going to zoom in for a moment on the O3 profile here. So again, in red is 93J, and in blue is Cassiopeia A. Notice, for instance, the large difference in the velocity span. And this is consistent with that reverse shock. It's going to be sampling ever slower velocities of the stellar debris. Okay? Notice here the substructure. Okay? In extragalactic supernovae, when we take late-time spectra of supernovae and we see these bumps, okay? People had often just the very scientifically precise term of blobs or clumps, right? And it gives the sense that this is kind of random material distributed unevenly. But in the case of Cassiopeia A, we actually know that it's not random. They're actually coherent, large-scale structure in Cassiopeia A. And if we could dim the lights for a second. So here, this is not a model, by the way. People see this and often come to me and say, oh, that's a great model you have. No, this is observed data. This is what Cassiopeia actually looks like in its reverse shocked material. And what we see, and this is going to rotate around again, I'm trying to emphasize a couple things. One is the interior bubble-like formations. This has been observed thanks to near-infrared observations where we could trace out the sulfur in the interior that match up, that connect with large-scale rings in the remnant. And if I could start the animation again right here. So here is a ring. There's a large ring in the back. Okay? And in fact, if I make a Mercator projection, hey, we're in the geological area, right? We make a Mercator projection of Cassiopeia A's reverse shock material, you can see that there are continents of rings, ejecta rings, and there's no shortage, there's no less than about 6 rings in total there. Those rings are reverse shocked bubbles, and the bubbles have an origin of which we can associate with nickel-rich plumes that worked out early in the explosion. And I know Tomas is going to discuss that, so I'm just going to look at this portion. Here's another instance where what we see in Cas A, which allows us a very close resolve view, does not coincide with the models being used in extragalactic cases. In blue is X-ray emitting iron-rich material, and in red is the optical sulfur and oxygen-rich. You can see that this iron-rich material is at the same velocity or even slightly ahead in certain regions of the main shell. Okay? Certain people would lead you to think that the X-ray emitting iron that we see today is broadly all of the is associated with all the nickel that was originally produced in the supernova that then decayed to cobalt and now in iron. And there's about 1/10 of a solar mass in, actually let's go back here, 1/10 of a solar mass of that iron that we can account for. That's about as much as iron as we would think a explosion like Cas A should make. And yet, we would assume that there would be much more iron interior to the 4,000 kilometers per second sphere. So original models using a type 2 progenitor system, right? So this is one with hydrogen, showed that if we could follow this line here, most of the production would peak at about 2,000 kilometers per second, right? Now we know that Cas A was hydrogen poor. And thanks to the work of many groups, including Tomas's great work, we can see that the progenitor into which the explosion proceeds into has a great influence in how that material moves. And it encourages, and this is a type 2 explosion, here we're following the nickel, you can see there's more of a flat distribution. The nickel can reach out to much higher distributions. So Cas A was great insight into understanding that there can be a great disturbance, a mixing, as it were, large-scale mixing of the nickel-rich material out to higher velocities than we would previously assume. Now, we got insight into this with 87A. Very early on, there was X-rays associated with nickel-rich material that had reached out earlier, but the extent to which we can see here in Cas A. All right, I see I'm again on time. Another aspect of Cas A that we can see only because it's nearby that may be lost in extragalactic cases. If you look at the right wavelengths and you stretch the image in the right way, you can see here in enhanced silicon, I talked about the northeast and southwest regions of high velocity material. The origin of this is disputed, and their importance is disputed even more. Okay? Some think of this as just a pimple. Originally thought that, hey, I think that there is just an inhomogeneous surrounding CSM, and there's underdensity in this area that allowed material to race out ahead. However, there are increasing evidence showing that that cannot be the case, and I'll speak to that in a moment here. So here's the northeast and southwest outflow. And here I've shown one of the papers where we've mapped it out. And again, it's not a highly collimated flow, so do not call it a jet per se, but more like a scatter. These are HST images spaced about a year apart. And because the material is racing so fast, we can actually watch the material move across the sky. Okay? There are literally thousands of ejecta knots. You can think of them almost as bullets. Let's enlarge a little bit more right here. Okay? And that's only spaced a year apart. Now what's remarkable is that the further out you go, the more metal-rich they become, which is to say closest to the main shell, they're nitrogen, oxygen-rich. As you move further out, increasingly sulfur, and there's no longer the nitrogen, and the oxygen is gone. And you move out even further, it's sulfur, calcium, argon-rich. Okay? So you get a real sense that material deep within the core was somehow shot out preferentially in these directions. And by the way, if I go, I think it's this plot that shows. So this is the axis of the jets. The inferred proper motion of the X-ray point source, the neutron star, is broadly perpendicular to this. Now, you can say, random, that's just happenstance. But at the same time, I phrase the question differently. How does the neutron star happen to know to go in the underdensity of the high-velocity material, right? We've looked very hard. There's no high-velocity material in this direction. So something special about that. Thank you. Okay. I'm having far too much fun with this. Okay, so thanks for your patience. Okay, so I didn't want to make this Cassiopeia-centric. I wanted to show that these ideas can be extended to other remnants. Here in the Small Magellanic Cloud, EO 102, timescales are different. This is about 340 years. This is of order 2,000 years. The work that my grad student is doing is kind of shaving off a few hundred years onto that estimate. Here is a 3D representation of the ejecta, and here is a kind of 2D projection of that. Once again, there is the broad ring-like or bubble-like distribution. Sorry, rings would be associated with the reverse shock. It's the bubble-like interior. So and then if I show another one here, recently published in Lopez and Feason, this is for another remnant, 3C58. You can see, again, this is the Mercator projection. We see rings associated in the ejecta. Now, it's an older remnant, much more perturbed by interaction with the surrounding circumstellar material, which is one of the consequences of working with remnants, but large-scale structure is still preserved. The takeaway point here is that though these remnants have very different chemical processes, elemental chemical abundances, the explosive processes seem to be broadly similar in that these large-scale bubble interiors have been preserved. Very good. Okay, I didn't want to make this only centered on core collapse supernova, so I wanted to have something about type 1a. Here's an interesting case of the supernova in M31. It was probably type 1a. I say probably because there is no published spectrum of it. There's only descriptions of it being hydrogen poor. So there's a type 1, but it could be many different streams. Let's just take for the case of argument that it was probably a type 1a explosion. Most of the evidence seems to favor that. Here we're seeing it not in emission. So the gases aren't being excited, but in this case, you have the bright light bulb of M31 bulge passing through cold material that's absorbing it. So here it is at the H and K lines. If we look at a continuum filter, okay, just a few hundred angstroms away, it's gone. I think that's the coolest thing. For decades, people tried to find the remnant in emission, but the secret was to look at it in absorption. And we look at it in absorption in different lines. Here it is in the calcium. Here it is now in the iron, and we see a broadly different distribution. Okay? In the interest of time, I'm just going to leave it at that. We see symmetric versus asymmetric, and if you read the Feason et al. Paper, they think that this is consistent, broadly speaking, with a roughly spherical delayed detonation explosion. Okay. The supernova remnant transition. So we talked about the connection. Where's the point at which we can see one go into another? Is Rabina in the audience here? I don't see her. Okay, I always like to highlight this because I used her data on 2004 ET to make this plot. Here is the supernova 400 days after explosion. Here it is about 800 days after explosion. You can see an incredible difference in the emission line profile. So again, this is the supernova. This is an unresolved source. You see all the ejecta simultaneously. And this sudden change, sudden is broadly speaking, is a result of the forward shock beginning to interact with the hydrogen-rich material of the supernova. So it goes from internal heating due to radioactive cobalt-56 to the reverse shock heating. And that is what I use, broadly speaking, in the sense of transition into the supernova remnant phase. Okay, and I'm going to go ahead because I have 1 minute. I had so much to go about. And then finally, we'll talk about this golden supernova. Just 2 minutes and I'll go into the question period. So this is another case where we're trying to make connections to the various types of supernova remnants that we see. 2012 AU, at one time I called it the golden supernova, which is a terrible name because people thought that there was gold in the supernova. It's not the case. It's just the chemical name AU. Late time observations that I'll show you in a moment, spectroscopic, were consistent with this being associated with the formation of a crab-like pulsar wind nebula. And I say crab-like because this explosion was a type 1b. It was an energetic type 1b. Here is the spectrum. Notice the absence of hydrogen. Notice that the velocity span of the line profiles are not like 4,000, 5,000, 6,000, or even large as we saw in O4 ET. They're much smaller. And so this, as well as the ionization level going up to O3, these components are all consistent with a pulsar wind nebula type remnant that's photoionizing the oxygen-rich material around it. At this stage, at a certain stage, at about 300 days post-explosion, the spectrum of 2012 AU was remarkably similar to a subset of superluminous supernova, the type 1s. And Matt Nickel, I saw in the audience, will speak more about that. And so 2012 AU itself was not superluminous, and yet its innards, which are being excited at the nebular stage, were very reminiscent of what is going on with a superluminous supernova. Now, one of the favored models of a superluminous supernova, where is it getting all this energy, is the energy input from a central source, a magnetar. So the thought is that this may be, 12 AU may be a nearby analog, much lower energy, of a higher energy superluminous supernova. All right, so just final concluding remarks. There's obviously rich science opportunities for connecting supernova to supernova remnants, and it applies with a lot of fields, as I stated in the beginning. I also tried to emphasize that detailed investigations of Cassiopeia are both consistent and divergent with what is broadly assumed about type 2b explosions. Okay, this extends to other types of supernovae as well. And then finally, a plug for where we're going in the future. I'm particularly excited about the next generation of extremely large telescopes. They're going to be able to get data of much higher quality, for which we'll be able to follow that transition from supernova to supernova remnant much more closely. We'll also be able to follow the evolution of the emission line profiles, which gives us information about the explosive energies and discriminating between the various central source energy systems. And that's all. I'll leave it at. Thank you very much.
Thank you very much for a great review. So we have time for 1 or 2 questions. Does anybody have questions for Dan? Yeah.
The silicon-enhanced spectrum you showed,
the image that you showed
Yes.
of silicon-enhanced Cassiopeia, I think it was. What wavelength and what transition of silicon was it?
So Vink is the one who made that, and it's a ratio between the magnesium and silicon lines. I don't know offhand those. That's X-ray. I don't know what
X-rays.
what energies that's at.
More questions for Dan? Yes, Kate.
So when you showed that low luminosity analog at the end, the superluminous supernova, you said it had to be a magnetar. I didn't quite understand why you think.
Oh, I didn't say it was a magnetar. So, sorry, a lower energy analog of a superluminous supernova. So, let's say a continuum of systems where there is a central object that's participating in the explosion. In the superluminous supernovae, the neutron star is going to have a very high magnetic field, magnetar, right? In this case, it's a pulsar, more consistent with energies for the crab.
Okay, and you're saying that's contributing to this spectrum then the 300 days.
So it contributed to, it participated in the original explosion that gave it the extra energy. So the energy of 2012 AU was about 10 to the 52 ergs, right?
Okay, thanks.
If there are no more questions, last chance. Yes, one more. That will be the final one.
For these normal luminosity analog of the supernova, do you probe the sulfur too? Because in the spectrum I cannot see that, but I remember I skimmed, or Alfred, your paper, and I remember you were mentioning a possible sulfur 2 around 92.
The sulfur 3 lines at 9069, 9531. That's exactly right.
That's the one.
That's right, yes.
And you saw that in 12 AU.
12 AU in the last spectrum that we saw.
Yeah.
That's right.
Yeah,
That's
because
at
we never saw
2008.
those in the superluminous.
Exactly, yes, yes. So, and let's be clear, there should be compositional differences between the systems. I'll give you that. And I'm curious to know what, well, I made the argument, I speculated that superluminous supernovae could then go through a similar change in emission, because at this point, the opacity has got, so we have this dense ejecta cloud that's expanding. The opacity has gone down enough that has allowed those X-rays to go through and photoionize the oxygen-rich layer. So perhaps if one waits around long enough in the superluminous supernova cases, a similar situation may happen.
So at least in some of them, yes, I do agree.
I agree.
Yeah.